Alrighty, guys, welcome to modules 2 and 3. This is the last set of modules for Unit 1, so let's jump in. Modules 2 and 3 is all going to be looking at biomes. We're first going to look at terrestrial or land biomes, and then we're going to jump in looking at aquatic biomes. Before we get started, of course, we have our objectives, essential knowledges, and skills. Okay, moving along. So when we're thinking about a biome, we are essentially looking at a region that is characterized by distinct temperature and precipitation yearly averages. And so when we're thinking about like our biomes, right, when you're comparing a tropical rainforest to a desert, very distinct patterns in terms of temperature and precipitation. And it's those two defining factors that define a biome. It is not, for example, animals in a region that defines a biome. A biome defines what animals and plants are there. It's not the animals and plants that define the biome. So let me say what I mean by that. There are plants and animals, such as cacti adapted to live in a desert, or sloth adapted to live in a rainforest, and they are going to be determined by the biome that they live in, right? But they do not define the biome. The biome is there first, and then the animals adapt essentially to live within that biome. So again, we do have those unique plants and animals, but the biome itself is defined primarily by what is the temperature averages and precipitation patterns, and then those then define what plants and animals end up living there. When we also look at biome characteristics, we can actually see that a lot of our biomes are along like a continuum. And again, those are those two defining features, averages in temperature, but also averages in precipitation for the year. And we can see that we have a lot of continuums going along here. For example, looking on my left-hand side, areas that are quite hot. Right? We've got our hot temperatures. I can go anywhere from a desert to a tropical rainforest. What's determining which biome I'm looking at least on this left-hand side, is those differences in precipitation. Low levels of precipitation, but hot temperatures is my desert. High levels of precipitation and high temperatures is my tropical rainforest. It's also cool. Again, okay, sorry, there it is. Haha, animal temperature precipitation. I know that my face is blocking this, but so I'm going to move it real quick so you can see, or I'll go ahead and say it. It says biome chart can also predict where on Earth biomes are found. So when we're looking at, again, our distribution of biomes across the world, we can see color-coded that they follow latitudinal regions, latitudinal organizations, right? So when I'm looking at, for example, my tundras in this light blue, we're looking right above the 60 degrees north. So our polar portions of the Earth's latitudes or the Earth's organization. So I can't think of my words sometimes. When we're looking at this light green, when I'm looking at my tropical seasonal forests, also known as my savannas, we're going right around the equator. So they are going to be distributed out based on temperatures, because that's going to also tie in as well, precipitations. So this is, again, just kind of defining them out by their regions, tundra versus temperate versus tropical. They follow along these continuums across our latitudes, across our planet. Latitude, of course, is our distance from the equator, and that's going to determine that temperature precipitation patterns. Okay, here's another way of looking at that continuum. So think about this as like another graph, right? We've got our x-axis on the bottom, looking at precipitation from very, very high moisture content on the left, and then we have dry content on the right. And then on the left-hand side, I have another axis or another continuum, and we're looking at temperature. So hot temperature at the bottom, cold temperature at the top. All this is showing us, though, is that my biomes are going along a continuum. For example, when I'm looking at these temperate regions, temperate parts of my globe, and again, that temperate latitudinal region of our planet, if I'm looking at, let's say, warm temperatures, not necessarily hot, but warm temperatures, but high levels of precipitation with warm temperatures in my deciduous forest, and if I follow that along my continuum to lower and lower levels of precipitation, I'm going to go from a chaparral, then to a grassland, and eventually to a desert as I decrease that precipitation, but keep it at that warm temperature. So again, biomes follow along a continuum. We're now going to jump into the biomes themselves. I always forget where my face is, so just in case you can't see, this first bullet point says temperature cold, seasonally variable. My tundra, when we're looking at this, we are looking at low precipitation and low temperatures. It's the lowest of both of those. So we're thinking Russia is my climatic graph over here. Because it is very low temperature, but also low precipitation, but mostly on the low temperatures, what I'm getting to on this is we're going to have a permanently frozen layer of soil known as permafrost. It is going to, parts of it are going to melt, especially as we're seeing our planet's temperatures change due to global warming. But in general, we're looking at this permanently frozen layer of soil Because of that, we're going to have very low levels of decomposition. If it's frozen, you can't really do anything. Nothing's really moving and grooving when you have low levels of temperature. So we're going to have low biodiversity, again, because of the low temperatures and low precipitation. Can't have a lot of plants. If you don't have a lot of plants, you're not going to have a lot of animals. So low biodiversity. Looking at my climatograph over here, this red line at the bottom is going to be my temperature for all of the graphs. The blue line on the top is going to be precipitation. You'll notice that these shaded green areas, those are going to be whenever we're actually having growth periods. And so we can notice that looking at my climatograph, the green period is only when temperature is above 0 degrees Celsius. If it's frozen, you can't really have a lot of growth because then the water is frozen, so you can't really take it in for photosynthesis if you're not having that precipitation, or if that precipitation is there, it freezes, right? So whenever we have the temperature below 0 degrees, we're not going to have growth. But anytime that it is above this line, that's when we're going to actually see that precipitation and that growth. Okay, moving along. Next up, we have the taiga. Again, my face is probably blocking it. This is our boreal forest, also known as the taiga. We're a little bit warmer. It's still not warm, but it's a little bit warmer in terms of our boreal forest. It's still subarctic, so it's still quite cold, but we are having a little bit more precipitation. We don't have still a lot of nutrients in this one because of that slow decomposition. A lot of this is because it's very cold. So think about metabolic processes. Metabolic processes are going to happen faster and they'll be more readily available when the temperature is warmer. Warm temperatures, faster cellular movement, but also metabolic processes. Cold temperatures, everything's slowing down. Your metabolism slowing down, cellular activity slowing down. Decomposition is the same way. When we have these cold temperatures, we'll have low levels of decomposition. Warm temperatures is going to favor that decomposition. So a little bit more precipitation, a little bit warmer in terms of temperature when we're looking at our boreal forest. So we are going to have higher biodiversity compared to the tundra. You can see it's a lot more lush looking. Over here is my boreal forest. Okay, next up, we're getting to our temperate rainforest. Already looking at the climatograph, I'm seeing a lot more growth. Precipitation is much, much higher. Biodiversity much more lush. And temperatures, we really don't go below 0. So we're going to be growing all months of the year, is what we're looking at here. That's where we see this green region occurring throughout all months of the year. Dark, moist interior, very humid interior because of these warm temperatures, but also this high levels of rain. It's not quite a tropical rainforest. It's not as hot or as much precipitation as a tropical rainforest, but it's on its way. It's still warmer compared to our previous biomes. So quite a lot of biodiversity, also a lot of decomposition. We're going to have very rich soil, very nutrient-rich soil because of these high levels of decomposition, because it's warm. These are mostly going to be occurring in our eastern coasts of our planet. So Chile, Pacific Northwest, looking at Alaska, not Alaska, sorry, that one's more taiga or tundra. Oh my goodness. Washington, my goodness. Washington and Oregon are going to be these parts. So in these warm coastal eastern, oh my gosh, I've been saying east. I'm so sorry, y'all. West is on the left. So Chile, western coast. Pacific Northwest, literally western coast. Oh my goodness, y'all. I'm so sorry. Okay, next up, we're getting to our temperate deciduous forest. Very similar, I would say, especially when we're looking at this climatograph, comparing our temperate deciduous forest to our temperate rainforest. Almost the same. Kind of the main difference is that we won't have as cold of temperatures when we're looking at our temperate deciduous forest, and it's more landlocked. And this one's usually going to be on the eastern coast. So we're looking at eastern United States, Japan on its eastern coast versus its western coast, which are temperate seasonal forests, which was our previous one. Precipitation stable. We're going to look at more darker forests in comparison to the last one. Still nutrient rich because of that warm temperature, favoring decomposition. Good biodiversity. This is what I'm usually thinking of, like a true forest. So we're thinking about when we have our black bears, we have our foxes, all of those, and our wolves. These are going to be part of our temperate deciduous forest. Next up, we have the chaparral, and now we're starting to get to lower levels of precipitation. First thing I want to point out is our climatograph over here on the left. We've got this yellow color. Yellow color is new. We are having essentially warmer temperatures that are always above 0. So we're never freezing in this one, However, we are going to have some dry periods, and dry periods are going to be denoted anytime that you see the climatograph go yellow. So whenever that precipitation line dips below temperature line, that means that precipitation, not temperature, is withholding and with restricting that plant growth. We are not having enough precipitation to actually have growth, even though my temperature is favorable in terms of that growth. So in this one, anytime you see yellow, think about dry periods. So when we're looking at from about April until about mid-October, almost November, these are going to be my dry periods. We are going to have quite a bit of moisture happening in my winter months. So the winter months are going to be my growing periods, but we're going to have these hot, dry summers, mild, rainy winters characteristic. I usually think about like desert scrubs. So you can see we've got some trees, but they're not tall trees. We have a lot of bushes, a lot of like kind of sagebrush is going on in the chaparral. Usually I think about like prairie dogs happening in the chaparral, and other smaller mammals in terms of what's going on in our chaparral. Moving on to our temperate grassland, these are going to be more of our central. Think about like the Great Plains. It literally says, yeah, sorry, Great Plains of North America. We've got a little bit of variation happening here. We are going to have some quite cold winters. There are going to be times when we dip below freezing in our winters. However, it is still going to be rainy during our winters. So that's going to be a lot of our moist when we have our growing periods. And we are going to have some variable dry conditions whenever that precipitation line dips below the temperature line. So in about May, early summer, and then late summer, July, August, September, we're going to have those dry periods. But thinking about, again, you can see in this picture, not a lot of trees, even less, I would say, than the chaparral. We have a lot of sagebrush, a lot of grass. We're having a lot of wheats going on here. A lot of corn grows well in temperate grassland. We're not having like lush forests in a temperate grassland. So a lot of flowering plants. Wildfires are very frequent here due to this very flammable material in terms of this grass. And because of these dry conditions in the summer, we do have a lot of that going on in the temperate grassland. Okay, next up, it's the one that everybody knows. We've got our tropical rainforest. You guys know this one, hot, wet. This is maxing out temperature, maxing out heat as well. When we're looking at these, it's pretty stable, like all year round. Hot temperatures and all year round, lots of moisture. One thing that might surprise you is that this actually is one of the biomes that has the lowest levels of soil fertility. Why would that be? We do have a lot of biodiversity, absolutely. But because there's so much biodiversity, because we are growing a ton all year round, we actually have high levels of competition. And so that ends up being why we have low levels of soil nutrient, because as soon as we have decomposition, which is favored in these warm temperatures, it essentially gets sapped up. The nutrients that are added into the soil due to decomposition taken up by the plants almost immediately because there's so much of them and there's high levels of competition. So again, this is going to be one where we have low levels of soil fertility, but high levels of biodiversity competing for those resources. All right, we are at our last two terrestrial biomes. Second to last one that we've got is our savanna. This is when I'm thinking Lion King, right? Hot temperatures, high levels of precipitation, but it is variable. It does depend on the seasons, okay? So when I'm looking at my climatograph, this is going to be our rainy winters once again. It flips it, okay, when we're looking at our climatograph. This is October here in the middle and April in the middle, okay? So we're going in our winter months, warm temperatures, which you might think is surprising, but think right around this, usually in the southern part of the equator. So that's not super, super surprising. And then we've got, actually, that's probably why it's flipped. Haha, southern hemisphere. Anyways, this is our growing season happening in what we would consider the winter. It's their summer is their winter. Sorry, our winter is their summer. There we go. It flips because it's in the southern hemisphere. We do have these dry periods occurring in other months. So from about April until October, it flips. Low levels of precipitation means that I'm going to have these dry conditions. Growth is not favored in this case. So pretty dry. It is still tropical, warm temperatures. It's above 10 degrees Celsius going up to our low 20s as well in terms of Celsius. Think about Lion King, right? We are going to have our lions and we're going to have our gazelles and our zebras, some trees, but a lot of grasses predominantly in these areas. Finally, we have our desert. We got to our last terrestrial biome. You guys know this one as well. Warm temperatures primarily, except for during our winter months, we are going to have pretty cold temperatures, and especially at night as well. Low levels of precipitation are going to align with low levels of humidity. Low levels of humidity, that cold air cuts through you, right? So we're going to have quite dry conditions most of the time. Precipitation is always below our temperature line on our climatograph, which means it's always precipitation that's holding back that plant growth. The plants, therefore, must be very well adapted. For example, last week we talked about the stomatas, right? Those small pores on the underside of plants used for gas exchange for photosynthesis and respiration. We said that water sneaks out of the stomata as well. That's why a lot of plants, including our cacti, have specially adapted leaves. So leaves on a cacti are the spines, like those pokey parts of cacti. That's their specially adapted leaves. And they're especially adapted to have really, really small stomata that really restrict that water loss that would normally occur from a full-size stomata in a full traditional leaf. So dry conditions all the way around, warm temperatures, especially during our summer months, but very low levels of precipitation. So in general, we talked about this briefly as we were going through our slides. Nutrient availability is going to essentially vary based on what that climate or what that biome is. Okay, plants need that soil nutrients in order to grow. So availability is going to determine what plants are there. For example, we talked about the tundra, which has frozen layers of soil, permafrost, which means very, very low levels of nutrients. Therefore, we're going to have plants that are specially adapted where they can survive when there's low soil nutrients and low water. It's very few plants, but the ones that are there have to have those adaptations. When we're looking at, again, our other variations in nutrient levels, we talked about earlier, tropical rainforest is nutrient poor soil, though it has that biodiversity because we have high levels of competition. Boreal forests are taiga, low nutrients because low temperatures. So decomposition is very, very slow due to the metabolic processes being slower in colder temperatures. But our temperate seasonal forests and our temperate deciduous forests, these are going to be doing great because it's warm, but it's not as much biodiversity as a tropical rainforest, so there's not as much competition. So it's favoring that decomposition without completely depleting those nutrients as they get in there. Alrighty, friends. Last part in terms of our terrestrial biomes is shifting biomes. We got to talk about climate change. It's apes, right? I know my face is probably blocking this. So this says biomes shift in location on Earth as climate changes. So as you guys know, probably from background knowledge, with warming climates, we're starting to see a shift in where our biomes are moving. So primarily, they're going to be moving to more northern latitudes. So while I used to have taigas and boreal forests, maybe in still above the 60 degrees latitude, they're now going to higher and higher latitudes as my planet as a whole is warming up. Remember, biomes are defined by temperature and precipitation. So in this graph here, we're looking at the suitability zone of aspen, with these dark colors being where the core, the majority of them are found, the tan colors being the entire range of where they could be. And as we can see, from the 70s to now, we are seeing this is kind of where they used to be, but the projected in the next 70 to 100 years, we're starting to see a more northern shift as our planet is moving. The taiga and our boreal forests, our taiga and our tundra are starting to shift more north, which means the aspen trees as well, which are in our taigas, are going to be moving north as well. We're actually already seeing this already. From the 1960s to 42 years later to 2004, we can see, kind of look out towards that water, where that little watering hole is. I'm seeing some aspen and some spruce, but not a ton. And then I compare that to 40 years later, we're seeing a lot more of those shifting up to these more northern regions. Of course, this is a very small field. We would imagine that this area used to not be as adapted for these trees, and now this area is becoming more suitable as its entire temperature is starting to warm. Okay, here's your practice FRQ if you would like to do it. Otherwise, we're shifting into our last part of Module 2 and 3. This is aquatic biomes. Before we jump into aquatic biomes, here's our essential knowledge and skills. Characteristics of aquatic biomes. There are 4 characteristics that are going to define our aquatic biomes: salinity, depth, flow rate, and temperature. Those 4 things are going to define if is it a salt marsh? Is it a bog? Is this a freshwater wetland? It all depends on, is there salt? How deep is it? What's that flow rate? And what are those temperatures like? So let's jump in. Fresh water is going to be our first one. As you can probably tell, not a lot of salt. No salt in our fresh waters. In terms of our fresh water, we have a couple of different types of freshwater biomes. These are rivers primarily, high levels of oxygen because they are fast flow rate. So it's churning that water. That oxygen is able to diffuse into that water very easily. So it's going to be high productivity with my aquatic plants, nutrient sediments, as we are starting to have decomposition, fertile soil happening in my fresh water. They are characterized usually by our lakes, which are standing bodies of fresh water. And we have some different key factors in terms of what's going on with our parts or anatomy of a lake. So there's 4 different components in terms of the anatomy of a lake, or zones, you can think of it. We have our littoral zone. This is going to be right along that coastline. This is where we're going to have emergent dominant plants because it's shallow enough that the soil is actually able to host plants. It's shallow enough that the plants are able to hook in, latch into that underwater soil, but then grow above the water as well. That's going to be our littoral shallow zone right there along the shore. Limnetic zone is going to be anywhere that the light can reach. So this is where we're going to be having photosynthesis. So we'll have some floating plants such as lily pads. We could also have some floating algae in the limnetic zone. Now this is going to be our photosynthetic area. Below the limnetic zone is going to be our profundal. This is too deep for sunlight. So this is going to be having no photosynthesis. It is where the sunlight cannot reach is our profundal zone. Finally, we have the benthic zone. This is going to be the lower portion. It is essentially the lake floor, whether it's very shallow in the littoral limnetic zone or very deep in the profundal zone. Anywhere where it is the floor of the lake, that is the benthic zone. So this is where we're going to have like our crawfish hanging out, our bugs, our invertebrates, all of those are going to be living in this benthic zone in the soil. Awesome. Continuing on with freshwater, we also have our wetlands. Wetlands are going to be characterized when the soil is submerged at least part of the year, submerged or saturated with water, but still shallow enough that we have those emergent plants such as reeds and cattails. Plants living here, they must be adapted to being okay with their roots being submerged in standing water. So you might notice that I didn't put succulents. As you guys know, the number one way to kill a succulent is overwatering. So they would not do well if their roots were submerged in water. So cattails, lily pads, reeds, all those are going to do really, really well in our freshwater wetlands. Benefits of wetlands, a ton. One, and we're going to have a whole day dedicated to the benefits of the wetlands. Don't you worry. But to give you a sneak peek, they store excess water when we have storms, so they're able to absorb that because their water is, or their soil is very porous. That a lot of water can infiltrate in. They're also going to recharge that groundwater as they have that infiltration, very porous. They're going to absorb in that infiltration part of the water cycle, and that's going to recharge my groundwater aquifer reserves below the water surface. We also are going to filter pollutants. They just do it all. As those pollutants, if they happen to get into this area, and as our plants, especially the root system, are absorbing it, they're able to absorb a lot of the pollutants and filter it out for us. Fantastic. What a great adaptation for my wetland plants to have, that they're able to filter these pollutants that come out. There might be one more. Nope, that was it. Okay, those were the benefits of the wetlands. Sweet. There are 3 primary forms of our freshwater wetlands. We have our swamp marsh, very wonderful. We can see we have mostly dominant trees in our swamps, but these are underwater trees, or trees that are okay and adapted with having the roots underwater. We're also going to have our marshes. Our marshes are going to have kind of our true lily pads, but also our reeds as well. You can see there's a lot of duckweed growing and some algae growing as well. And finally, we can also, oops, what does that say? Reeds and cattails is that box that you can't see. And then we also have our bog. Bog is going to have a lot of sphagnum moss, and it's going to have a lot of peat moss as well. Very spongy material that's going to be absorbing and filtering, and honestly, taking in a lot of CO2. We'll learn about them when we get to climate change, but bogs are the key. In my opinion, bogs are the key to like helping global warming because they absorb so much CO2 and they just really hold on to it. They don't respire a lot of it back into the atmosphere, which is great. So this is again our spruce and our sphagnum moss. Okay. Estuaries is a special subcategory of our freshwater wetlands where they actually have rivers emptying into ocean. So you have freshwater meeting saltwater. So our species, such as our mangrove trees, have to be specially adapted to essentially handle both freshwater and saltwater. They can do it all. They're just the superheroes of our trees. High productivity because we have a lot of nutrients that are running off and being transported by the rivers. We're going to be learning in class that we have our watersheds, which is a network of rivers at high elevation, bringing things down to our larger bodies of water at lower elevation. And they're bringing in all those nutrients from all these rivers and all these deltas are dumping into these estuaries. And so it is a very nutrient-rich party going on within these estuaries. Salt marsh is going to be a great example of this, where we have an estuary, this wetland, where the river is meeting the ocean. A lot of fish and shellfish. We always probably think about crabs as a really big indicator species of our salt marshes. But we also have mangrove swamps. And mangrove swamps, if you're not a fan of a mangrove swamp, get ready. Some people think about Shrek, which is funny. Like, that's a swamp. Okay. Anyways, these are going to be across our tropical, so a little bit warmer compared to our salt marshes, which are more temperate. So a little bit higher elevations or higher latitudes. For my salt marshes, mangrove swamps are going to be a little bit warmer there. Mangrove trees, because they are trees, they're going to have very intricate and very well-established root systems. And these roots are amazing. They can stabilize the shoreline. They can hold in that soil so we're not having erosion of that shoreline into our waterways. And they can also reduce flooding, and they can reduce the effects of storms. You're like, how can that happen? How can a tree reduce the impact of a storm? Stay tuned for the next video. Okay. Mangrove swamps protect coastlines from tsunamis, cyclones, and storms. This is a demo here. I'm just going to show you guys real quick, but they are trying to illustrate if we have a storm and that storm is coming through, we have a model of a mangrove swamp with those mangrove trees right there, and we look upstream of those, we see very little, I guess, flow influx that's happening there. So again, these mangrove swamps are shelter belts. They are the protectors against storms. They are protectors against tsunamis. I can't say enough great things about the mangrove swamp. You should pick that for your project. Okay, we'll explain that later in class though. Okay, how do I leave? Okay, we got our last couple biomes in terms of our aquatic ecosystems. We have our coral reef. Everybody knows in the coral reef, warm tropical areas, shallow waters, very diverse. It's the most diverse marine ocean ecosystem because there is a lot of biodiversity due to these warm temperatures, but also there's so many plants as well. Plants and animals that host a lot of fish, high biodiversity going on here. There is a mutualistic win-win relationship between the coral and algae. We'll learn about this when we get into climate change. But algae actually live within coral. Algae is what gives coral their color. What happens is that the coral is going to take CO2 out to create calcium carbonate, which provides a home for the algae. And in return, the algae are going to be supplying nutrients and stability for the algae, for the coral itself. When we talk about coral bleaching, that's actually coral that has become brittle because they've lost the algae. The algae is crucial in terms of stabilizing that coral, and in return, the coral provide a home for the algae. It's a win-win relationship for the two of them. Sorry, that's exactly what I said. Algae live in the reef, they provide sugar or energy to the coral. Both species rely on each other. The coral is extremely debilitated when it doesn't have the algae, and the algae need the coral in terms of having a home, and that way they can also obtain carbon dioxide from the coral. Intertidal zones, I think this might be our last or second to last one. These are going to be coastlines when we have high variation between high tide and low tide. So usually compared to a coral reef, which is below the water surface, intertidal zones are going to be along coastlines, especially coastlines that have a steep slope or incline. We got to have a lot of special plants and a lot of special animals. They have to survive crashing waves, direct sunlight, heat. They can't be scorched. They need to be able to survive some of their time below the water surface when we have high tide, but they also have to survive time periods when they are up above the water surface. When that water goes down, can you survive without water? They've got to be able to live with and without water. Our sea stars and barnacles, they can live both with and without water, and they can survive the intense heat whenever there's low tide, but they can also survive the time when they are submerged underwater. Usually they have adaptations such as tough outer skin and shells that prevents them from drying out during these low tide periods. When we're looking at ours, again, different ones are going to be adapted to different regions. There are some organisms such as our limpets, which are going to spend most of the time out of the water. They're just going to get splashed. They're quite literally in the splash zone. They need to survive some water, but not a lot. Same thing with our barnacles. They're in the high tide zone, so they're going to still get some, but they're not going to get as much water as our mussels and anemones, and our low tide, such as our kelp forests. So the ones that are down below, they need to be adapted to spend most of their time underwater and some time above water. My high tide organisms must be able to spend most of their time, they're adapted to spend most of their time in the heat with these oh my goodness, these low tide events. They don't have a lot of time that's going to be actually underwater. I appreciate y'all's patience. I know I've just been word salading here a little bit. Okay, last one that we've got is the open ocean. Low levels of productivity because really we don't have a lot of soil. Only the soil that we have really in our oceans are going to be way down on the ocean floor. And in the ocean floor, you don't have sunlight, so you don't have photosynthesis. So really, we've just got like floating algae. And that's pretty much the only plants that we have going on in my open ocean. Our kelp is going to be in our more shallow and what we call the continental shelf. But in our deep open ocean, we're not really having a lot of productivity. However, because our oceans make up 70% of our oceans or of our planet's surface, the algae that is there and the phytoplankton that is there produce so much oxygen and they absorb so much CO2 that it's definitely, you can't sleep on the open ocean. They're doing a lot of good stuff for us. We're going to have different regions and zones similar to our lakes. We have our photic zone where photosynthesis occurs. This is the area where sunlight can reach. And we have our aphotic zone, no light zone. This is whenever it's too deep for that sunlight to actually reach. We do have some chemical processes going on. Chemosynthesis is going to be done by my bacteria below the surface. So we are having some metabolic processes happening. It's just not photosynthesis itself. We can still create energy through chemosynthesis, usually a lot of times from the sulfur vents, what's released from our sulfur vents on the ocean floor, but we're not having photosynthesis happening here. Because of that, because there's no light, we do have to have organisms that are specially adapted, such as everybody knows the anglerfish from Finding Nemo. They have to be specially adapted to having no light or being able, if there happens to be a sliver of light, being able to utilize it. So they've specialized eye sockets or specialized senses in order to navigate and get around. I wanted to really quick say this is also the benthic zone, just like in the lakes. That's going to be any time that it's the actual floor of the ocean, whether it's on this continental shelf or it's in the benthic, the aphotic below the open ocean floor. You've made it to the very end. Finally, this is the last part of Unit 1. Congratulations. Here is your FRQ. I hope you guys have a wonderful rest of your day, and I will see you guys in class. Take care.